multiplication without binomial expansion. Watch what happens to open parenthesis 1 plus I close parenthesis to the nth. At first it seems like it should only get bigger, but in the complex plane it also rotates. Compare that to real numbers. Multiply by 2 and a point moves farther from 0. 1, 2, 4. The length changes but the direction stays the same. Now multiply by 1 plus I. That changes both magnitude and angle. It stretches the vector and turns it. So repeated multiplication does not stay on a line. It grows while rotating, creating a spiral. Now let's explore this using matrices, powers, and the matrix exponential. Watch what happens when we keep multiplying by open parenthesis 1 plus I close parenthesis. We start with z equals 1 plus I. On the complex plane, each multiplication does two things at once. It rotates the vector by 45 degrees and scales its length by square root of 2. So z becomes z squared, then z cubed, then z to the fourth. And the pattern is not random. The angle keeps increasing, 45 degrees, 90 degrees, 135 degrees, 180 degrees. At the same time, the length keeps growing, square root of 2, 2 to square root of 2, 4. That is the key idea. Complex multiplication is scaling plus rotation. And that is exactly why repeated powers trace a spiral. Let's build the bridge from complex numbers to matrices. Start with a complex number, z equals a plus bi. Now take any point on the complex plane, x plus yi, and rewrite it as a vector, xy. What happens when we multiply? Open parenthesis a plus bi close parenthesis times, open parenthesis x plus yi close parenthesis, expand it, then group the real and imaginary parts. You get x prime equals ax minus by, and y prime equals bx plus ay. That means complex multiplication acts like a linear transformation. So we can represent z equals a plus bi by a matrix. Open bracket a minus b, b a close bracket. And now the key idea, multiplying by a complex number is the same as applying this matrix to the vector xy. This is the matrix isomorphism, the bridge that lets us study complex powers using matrix powers. Now let's test the matrix bridge with a real example. We will multiply open parenthesis 2 plus I close parenthesis by open parenthesis 1 plus 3, I close parenthesis in two different ways. On the left, we use ordinary complex algebra, expand, combine like terms, and use I squared equals minus 1. That gives us the complex result, minus 1 plus 7i. On the right, we convert each complex number into its matrix form, then multiply the two matrices. After the matrix multiplication, we get a new matrix, open bracket minus 1 minus 7, 7 minus 1 close bracket, and that matrix matches the same complex number minus 1 plus 7i, so both paths agree. This is the key checkpoint. Complex multiplication and matrix multiplication are giving the exact same structure. Now we convert the matrix form into polar form. Start with z equals a plus bi, and write its components using trigonometry, a equals r cosine theta, and b equals r sine theta. That means the same complex number can be described by a length r and an angle theta. Now substitute those into the matrix form, open bracket a minus b, b a close bracket. The result becomes r times a rotation matrix, cosine theta minus sine theta, cosine theta. This is the key geometric step. Now we prove de Moivre's formula using matrix powers. Start with the polar matrix form, m equals r times the rotation matrix with cosine theta minus sine theta, cosine theta. First, square it. When we multiply m by itself, the scale becomes r squared, and the angle terms combine into cosine 2 theta and sine 2 theta. Now cube it, multiply m squared by m, and the scale becomes r cubed. The trigonometric terms combine again, now giving cosine 3 theta and sine 3 theta. So the pattern is clear. Every time we raise the matrix to a power n, the magnitude becomes r to the n, and the angle becomes n theta. That gives the matrix form of de Moivre, and therefore the complex form z to the n equals r to the n times, on parenthesis, cosine n theta plus I sine n theta, close parenthesis. Now let's go one level deeper, the matrix exponential. We start with the special matrix J, the matrix version of I 0, minus 1, 1, 0. Geometrically, J rotates a vector by 90 degrees. Apply it once and 1 becomes I. Apply it twice and J squared equals minus I. That repeating pattern is the key. Now build the exponential e to the j theta. Using the Taylor series, the even powers group into cosine and the odd powers group into sine. So the matrix exponential becomes cosine theta minus sine theta, cosine theta. That is exactly the rotation matrix. And here is the beautiful connection. The matrix formula mirrors Euler's formula, e to the I theta equals cosine theta plus I sine theta. So complex rotation and matrix rotation are the same structure. Now let's conclude with two matrix methods for open parenthesis, 1+i close parenthesis to the eighth. First, the direct power method. Represent 1+i by matrix A, 1 minus 1, 1, 1, square it. A squared equals 2j, where j is 0, minus 1, 1, 0. Since j squared equals minus I, we get a to the fourth equals minus 4i, and a to the eighth equals 16i. So open parenthesis 1+i close parenthesis to the eighth equals 16. Second, the exponential method. Write a as square root of 2 times e to the open parenthesis pi over 4 close parenthesis j. Raised to the eighth, 16 times e to the 2 pi j, and e to the 2 pi j equals I. So again, open parenthesis 1+i close parenthesis to the eighth equals 16. Thanks for watching.